Okay, let's take a look at Le Chatelier's principle. For GCSEs, you don't need to know the name Le Chatelier. You just need to know the process, basically the thing that it encompasses. But it's good to know the name anyways. Okay, so Le Chatelier's principle is all about the position of the equilibrium in reversible reactions and how they can change due to temperature. So the first factor, which is temperature. Second factor, pressure. And the third factor, concentration. So changing any one of these three things could shift the equilibrium either towards the product side or backwards toward the reactant side. Temperature, pressure, and concentration. And by the way, reversible reactions can only occur in a closed system. Because imagine you had a reversible, remember the symbol for reversible reactions look like this. Imagine you had your reversible reaction and your products are being formed. If it was an open system, your product would just leave. There would be no products that can turn back into your reactants. So reversible reactions, and therefore equilibrium too, can only be reached within a closed system. So nothing can enter, nothing can leave. No energy can enter, no energy can leave. Three factors: temperature, pressure, and concentration. So let's take a look at temperature first. Previously you stated that equilibrium lies towards whichever side has more. Okay, this isn't specific to temperature, but if we change the conditions of a reversible, so for example, if you had a reversible reaction and you had, 5 moles of your reactants and 10 moles of your products, the equilibrium is going to lie closer towards whichever side has more. So the equilibrium will lie closer towards here. But the position of an equilibrium can change because of these three factors changing within a reversible reaction once it has started. So first of all, changing the temperature. Let's take a look at an example. We might have nitrogen plus hydrogen, and the reversible reaction is going to go from nitrogen NH3, so ammonia, and this entire reaction is 92 kilojoules per mole. Let me write that in a bit more clear way. This minus 92 is really important, more specifically this minus symbol over here. This shows us that this forward reaction is exothermic because it's showing us the energy change of the overall forward reaction. Minus 92 kilojoules. It means 92 kilojoules are being released in the forward reaction. So this means that the forward reaction is exothermic. Remember, you can remember exo and endothermic reactions easily by saying exo kind of sounds like exit, right? So energy exits, endo enters, so energy enters. So the reverse reaction, remember, one side is exo, one side is endo. It can't both be one. So if one is exo, other has to be endo, and vice versa. Because it's a minus, it shows us that the forward reaction is exothermic and the reverse reaction is endothermic. So since the energy change is negative 92 kilojoules per mole, the negative shows us the forward reaction is exothermic, releasing energy. And the backward reaction has to be the opposite of that, so it must be endothermic, hence absorbing energy. Assuming the equilibrium for this reaction is currently lying in the middle, assuming it's already at equilibrium in the middle, what would happen if we changed the factor of temperature? One factor is if we decrease the temperature, and the other factor is if we increase the temperature. Now the confusing thing about this temperature section is it differs whether the reaction is exothermic or endothermic. Let's assume the reaction is exothermic first, and let's see what would happen. Let's think about decreasing the temperature first. What if we decrease the temperature of the reaction? So this might be a bit hard to visualize. Imagine the reaction is occurring within a sealed box. If the reversible reaction is all occurring within a sealed box, when I say decrease the temperature, I mean the entire temperature within the box is decreasing. Not just the forward or the reversible, the entire temperature of the container, of the place where the reaction is occurring is decreasing. That's what I mean when I say decrease. When I say increase, you're in a closed system and the entire temperature of this closed system is going to increase. So assuming that the reaction is exothermic, when we say exo and endo, we're always talking about the forward reaction, by the way. So assuming the reaction is exothermic and we decrease the temperature, what would happen? We can currently visualize this reaction like this. We have A, the reactants, and we can make heat become one of either the reactants or the products. So we're going to have our product B formed regardless of heat, right? But since it's an exothermic reaction, the product is going to be heat, releasing heat, right? So one of the products can be said to be heat. It's not going to be a reactant because it's an exothermic reaction. Likewise, if the reaction was endothermic, then one of the products would be heat as well. So A plus heat would go to form our product B. Let's go back to our exothermic reaction though. So we're decreasing the temperature. A reactant goes to form our products and heat since it's exothermic. Therefore, if the temperature of this entire reaction decreases, right? We're talking about the whole thing. If the whole thing, the temperature decreases, there's obviously going to be less heat in the product section, right? So the equilibrium will have to shift right to even out the heat. So if the equilibrium was at the middle, it's now going to shift right. It's going to lie towards the right to even out the heat. Does that kind of make sense? It should make sense, right? Products and reactants. Since you're decreasing the temperature, you're going to have less heat being produced as part of your products. So to speed that up, your equilibrium is going to shift towards the right. What if you increase the temperature in an endothermic reaction? So we're going to increase the temperature in an endothermic reaction, and we're going to assume equilibrium is currently lying in the middle. So what if temperature increased? Well, since heat is one of our products of our reaction, if the temperature increased further, there would be a lot of heat on the product side, right? We'd have even more heat on our product side. Therefore, the equilibrium would have to shift left, the opposite direction, to kind of balance out the heat. Therefore, the equilibrium would shift left so that you can even out the heat on either side of the reaction. It's sort of common sense. Then let's look at endothermic reactions. Endothermic reactions require heat for the forward reaction to take place. So one of our reactants is going to be heat. Then, if we decrease the temperature, what would happen? If the temperature decreases, so if the temperature decreases, there would be less heat on the reactant side, right? Remember, this is all happening within one enclosed box. So if the temperature within this entire box decreases, there's going to be less heat on the reactant side. And hence, equilibrium would have to shift left to even out the heat. So the equilibrium would shift towards the left. Likewise, if the temperature increased, what would happen? We would have our reactants of A plus our heat, reversible reaction to form our product of B, right? If the temperature increased, there would be even more heat on our reactant side. We're going to have even more of this. And therefore, equilibrium would need to shift towards the right in order to balance and even out the heat. So in simple terms, just consider heat to be one of either the reactants or the products. Just make a simple equation like this. And just imagine, depending on whether your reaction is endothermic or exothermic, just imagine what would happen to the heat. And then just balance the heat out in the opposite direction to make an equilibrium. Let's look at our second factor. Our second factor is changing the pressure. So number 2, changing the pressure. Now don't worry, the changing the pressure part is the easiest. It's the second easiest, honestly. We're going in descending orders of difficulty. The hardest part is out of your way. Changing the pressure. This one's simple. It doesn't matter whether your reaction is endothermic or exothermic, it's going to stay constant. So no need to worry about that. If pressure increases, equilibrium is going to shift towards whichever side reduces the pressure back down. If pressure decreases, equilibrium is going to shift towards whichever side raises the pressure back up. And the side is determined by the number of moles on the reactant and the product side. For example, we could have nitrogen again reacting with hydrogen, going to form a reversible reaction of ammonia, right? Let's balance out our equation. And we can tell the number of moles by looking at the number in front. This N2 just means it's a 1. There's 1 mole there. We simplify it out. It's kind of like algebra. When you have 1A, you just simplify out the 1, and you just write A. So in the same way, it's N2. Don't mistake this for 2 nitrogens. This just means we have 2 nitrogen atoms bonded together, forming 1 molecule of nitrogen. Remember, nitrogen is a diatomic molecule. We have 1 mole of nitrogen, 3 moles of hydrogen, and 2 moles of ammonia. Just don't look at these tiny numbers. That's just telling us the structure of the molecule or the compound. 1 nitrogen, 3 hydrogens, and 2 ammonia, sorry. That means our reactant side has 4 moles in total, 1 plus 3 moles. Our product side has 2 moles in totals, just 2 moles of ammonia, right? And remember, we said that the side is determined by the number of moles on the reactant and product side. So this time, the reactant side has 2 greater moles than the product side. Therefore, what would happen if pressure increases? If pressure goes up, what would happen? Equilibrium is going to shift towards the side with the fewer moles. And in this case, that's going to be the right side, right? So equilibrium is going to shift right. Equilibrium shifts right. What if pressure decreases? It's simply going to be the opposite. Equilibrium's going to shift to the side. So this time it's going to be the left side. Equilibrium shifts right, equilibrium shifts left. Think. It would be easier to raise the pressure by adding to where there's lots, right? So pressure is just about how much particles there are within a given space, right? You can just try to visualize this. If the pressure of the overall container increases, if you shift towards the side with fewer moles, you're going to have less pressure overall, right? So your equilibrium is going to shift towards the sides with fewer moles. If pressure decreases, you're going to want to raise the pressure back up. It's easier to go towards the side with more things, to just add a bit more to the side with more, right? So equilibrium is going to shift left or towards the side with more moles. So for example, if this side had 2 moles this time, and if this side has 4 moles, this part is completely invalid now. The reactants have 2 moles, products have 4 moles. If pressure increases, then what side is the equilibrium going to shift? It's going to shift towards the side with fewer moles, right? So it's going to shift left. If pressure decreases, it's going to shift towards the side with more moles to raise the pressure back up, right? So equilibrium is going to shift right. You just need to kind of use common sense and think this through. The last bit is the easiest of the 3, changing the concentration. This bit is just basically, just imagine a scale. And you have a scale of your reversible reaction. And you have your reactants on one side, and your products on your other side. If, let's say, you have 10 moles of reactants and 20 moles of your products, you're going to have more things on your right side, right? So equilibrium is going to shift towards the side with less to even out the weight. If this time your reactants had 20 moles and here you have 10 moles, equilibrium will shift towards the right, the side with fewer things, to even out the weight again. Just think of it as a scale. If you add, it'll go towards the side with fewer so that you can even out the weight. If you take away moles, it'll go towards the side with, again, less things to even out the weight. That's pretty much all you have to know about Le Chatelier's principle. Temperature. If you increase the temperature, what happens? If you decrease the temperature, what happens? And remember, it differs whether it's exo or endothermic. If you change the pressure, it goes towards the side. Just kind of use common sense again. Equilibrium shifts left if you increase the pressure this time, because you have fewer moles on this side. It's going to go towards the side, which is going to be easiest to reduce the pressure back down. If your pressure decreases, you're going to go towards the side with more moles, because it's going to be easier to raise something where there's already a lot more things in there, right? Changing the concentration, it just goes towards the side with less, because you want to even out the scale and make it a balanced scale. That's it for Le Chatelier's principle, and I hope this helped.